All right, hi everyone. So, welcome to the lecture 2 of chapter 11. So we're gonna continue on with our bonding theories. So remember, we've already gone over the Sieper theory, right? In chapter 11, that was to tell, what shapes the molecules are in 3 dimensions, because Lewis structure only allows you to do 2 dimensions, right? We're gonna continue with that. And remember, I'd mentioned that, these theories have boundary of where they start to not work so well anymore, right? So the problems with Lewis theory is that, it generally predicts trends in properties, but doesn't give good numerical predictions like how strong the bond is or how long it is. Lewis theory only gives good first approximations of bond angles, but usually it's quite off from experimental data. Lewis theory cannot write one correct structure, and you need a lot of resonance structures, right? If you guys remember. And then finally, Lewis theory is not able to predict magnetic behavior of molecules. Um, so that's why we need um, another theory, right? Um, this one is valence bond theory that we're gonna learn next, and it's gonna look, similar to it's building off of Lewis theory, right? All these theories they need to be congruent with each other. They cannot um, contradict each other, right? It's more of like an addition, an extension of the other theories, right? Than like a completely different theory, right? It still keeps some of um, the the parts of another theory. You'll see similarities, and then you also see additions, right? It's able to make more predictions. So valence bond theory approaches chemical bonding based on the extension of the quantum mechanical model. And that's when orbitals interact, they make a bond, right? And so now we are thinking, in Lewis theory, we were thinking in terms of um, just the valence electrons and the electrons pairing and making octet, right? We didn't really go into details, like actually how it does that. So valence bond theory is much better at explaining what, really is happening on the atomic level is that the orbitals are actually overlapping with each other, okay, to form a bond. So these orbitals that are interacting with each other, they're called hybridized atomic orbitals. And it's like putting atomic orbitals in a blender and getting a hybrid orbital. So in mathematical terms, that's just basically, constructive interference of the waves, right? Um, so we don't have to do the math, but you're going to see how orbitals hybridize and then what we call the new hybrid orbitals. And that's pretty easy. It does not involve any, um, fancy math, but that's actually where it comes from, right? So this is how you want to think of bonding now. Sort of a more complete understanding, right? It's not just two electrons make a bond. Yes, that's the basis of it, but like where are the two electrons and how are they interacting with each other? You can imagine, let's say two hydrogen atoms. Let's look at picture 1 here. Two hydrogen atoms, right? The dots are the nucleus, so 1 proton. And then the blue cloud, that's your 1 electron just moving all over the place, right? So if you have two separate hydrogen atoms, right? Why don't they stay separate? We know that hydrogen element is H2. So one hydrogen atom likes to bond with another. And what is the impetus for that? Well, remember that the proton of one hydrogen atom is going to attract the electron cloud of the other and vice versa. So you have a mutual attraction already, that is plus minus, right? But then you have to also consider the repulsion, right? So as these two atoms come closer together, you see this red line, energy is going up, right? So the red line goes down, which means you get a stabilization of energy as the two hydrogen atoms come together. But if they get too close to each other, then what you get is you increase the electron repulsion and the nucleus repulsion. So the atoms can't get too close before the potential energy rises again. Okay. So at one point here, there's an optimum distance that the two nuclei are from each other. And that optimum distance is where you have an energy well, right? That's what we call it, because that's the lowest point in energy, in potential energy, and that's the most stable, most optimum spot for the two hydrogens to be, right? And that's actually what defines a bond strength and a bond length for any two atoms that are, you know, in a bond like this, right? So what is that sweet spot where you have the lowest potential energy is what defines your bond length and also your bond strength, right? And remember, the shorter the bond, the stronger the bond, the longer the bond, the weaker the bond, right? So in picture 3 here, that's where we have this sort of optimum distance, right? Too far apart, then the energy is high. Too close together, then the energy is high. But here's the sweet spot. Okay, so what's actually happening here, as you can see in the picture, you see this overlap, right? You basically, one hydrogen atom is fusing into another. This is what we call the orbital overlap, right? It's a 1s orbital of one hydrogen and a 1s orbital of the other, and they're actually in each other's space, um, uh, forming this low energy region where these shared electrons can be, right? And so that's basic. That's the basis of valence bond theory, right? Is these orbital overlap. So as the two atoms approach each other, these atomic orbitals, you know, get together, they kind of interact, right? They overlap to form what are molecular orbitals. So that's the region of high probability of finding the shared electrons in the molecule, right? And that will happen with, you know, any two atoms, right? Um, they will make a molecular orbital region where you most likely find the electron density due to it being the most stable. Okay. So let's look at an example of like a very simple example of valence bond theory with this molecule H2S. Okay, so for H2S, two hydrogen attached to a sulfur, when you draw these orbital diagram, that's what you see here. That's what it's called, orbital diagram, because it showcases which orbitals are involved in the bonding. But before you start drawing the orbital diagram, what you want to do first is draw the orbital. Sorry, this is the bonding scheme. Bonding scheme, not orbital diagram. The one on the left is orbital diagram. So to get the bonding scheme here, you need to start with the orbital diagram of all of the atoms involved. So you're going to start with hydrogen, NsB1s1, right? We all know that. So one box for the 1s, put the 1 electron in it. We have two hydrogens, right? So sulfur, right? Look on your periodic table, 3s2, 3p4. You do not have to do the full configuration, right? Just the valence electrons, and this is where it overlaps with Lewis theory, right? It's only the valence electrons that are involved in the bonding. So again, right? 3s2, 3p4. So that's how you would fill it out. And remember that Lewis theory says it's the unpaired electrons that are going to be involved in bonding, right? So once you have your orbital diagram, you know exactly which orbitals are going to be involved in the bonding. It's these two here and not this one, okay? So you can see that, let me get my pen going here. You can see all of these orbitals represented. So if we look at the S, the blue sphere is the 3s orbital, okay? Remember, s orbital is spherical shape, okay? So the 3s is that blue ball, okay? And it's got two electrons, or has a pair of electron up and down, okay? Then these red balloons, okay, it belongs to, remember the 3p orbitals, right? Remember in the p subshell, there are 3p orbitals. It's a px, the middle one is a py, right? And the last one's a pz. This is why you guys had that quiz where you drew all the orbitals. This is where it comes in handy to know your orbitals, right? That's a z, by the way, px, py, pz. So let's call this the x-axis. So let's say that this, remember what the p orbital looks like? It's a peanut, right? So this whole thing, this part right here is the px, and I'll call this one the py. That's y-axis, right? It's going diagonal like that. So this whole thing is the py orbital of the sulfur. And then the one up and down, right? The peanut that is up and down is pz. So notice you always draw, right? You always imagine that the central atom is exactly in the middle here. Okay, so in the px orbital, well, here it shows the pz orbital as having a lone pair, but it doesn't matter how you name it, right? It's that one of the p orbital has a lone pair and the other two have single occupied So that's the one that's going to make the bond with hydrogen, right? And hydrogen's 1s is represented by this sphere. Like that, right? So hydrogen brings in its 1 electron, right? And it's going to pair with the sulfur's py, right? This one single electron. Okay. And then the other hydrogen with its 1 electron will also go and pair with the other p orbital of sulfur. Okay. And then the third orbital is not bonding to anybody. Why? Because it's a lone pair already, right? So this here shows the power of valence bond theory. Lewis structure wouldn't be able to predict this, because if you were to draw the Lewis structure, right, it would be sulfur. It's got single bonded to hydrogen, single bonded to hydrogen, and then 2 lone pairs, right? Well, if this is how you would draw the Lewis structure, Lewis theory would predict that this angle right here is 105. Remember that? Because you have sulfur and tetrahedral and you got 2 lone pairs. So it would have predicted H2S to have 105. Okay. And that would have been wrong. Okay. Because look, valence bond theory predicts that it would be 90, right? Why? Because remember, all the p orbitals are lying on the Cartesian coordinate and they're all 90 degrees apart. So this angle right here is actually 90. So valence bond theory here does predict a 90-degree. And that's very different than what Lewis theory would predict, right? And the actual bond angle, what we do measure, is 92. So obviously it's the valence bond theory that is superior here in predicting bond angles, right? So this is what I mean. Like, you have, a theory that doesn't do as well with bond angle, right? It serves other purposes. Lewis structures are very simple, right, and quick, but it breaks down in other places. So when it comes to bond angle, valence bond theory is the superior model, right? Okay, so that's the basis valence bond theory there. You can see that you have overlap here. See this region of overlap? That's what we call the molecular orbital, and that's where the electrons, the shared electrons, are most likely going to be, right? Okay, so now let's go to CH4 and see how we draw CH4 using valence bond theory. I'll do this on the board. And this is a great example to show why carbon needs to now hybridize. And in the last case, in H2S, we didn't have to worry about that, right? But here I can show you why carbon needs to hybridize. And also, what does hybridization mean? All right. So I would always start with the Lewis structure first, right? That's the reason why we learned that theory. Um, it's helpful to know what the bonds are so that you can do your bonding scheme off of your 3D Lewis structure. And it should be 3D. I think it works better, right? So we have CH4, that's 4 plus 4 times 1, right? 8 valence electrons. It's going to look like this. Okay. 2, 4, 6, 8. Okay. And now we determine the number of electron groups, right? So that's 1, 2, 3, 4. So 4 electron groups. We know it should be tetrahedral. Okay. But here, if we look at carbon's orbital diagram, okay, we would say 2s 2 2p2, right? That's carbon. Yep, 2s2 2p2. And then hydrogen, right, of course, is 1s1. Okay. So now I put these orbitals on top of carbon, just like we did with the H2S example. Okay, we're just gonna put the atomic orbitals of carbon on there. So the 2s, remember the s is just a circle. So this is your nucleus, right? So just draw your circle around there. You can call this the 2s, right? And it has right now a lone pair in it, so you can show that as well. Then you go over here to the 2p, it's 2p2. And remember, first box, second box, third box, x, y, z. Keep it simple, right? Just like it. So from left to right, px, py, and pz. So in the px, and I always, I always do like to do the x direction. Well, it doesn't matter how you do it. I kind of like to do it like that. There's my px. I'll call this my py. And remember, the p orbital is a peanut, right? So this is one part of the peanut, and that's the other part of the peanut. So the px orbital is this whole thing, right? So this is still the same orbital, right? These two lobes. And same here, this whole piece is the py, okay? And then this one is the pc. So notice that the px has one electron in it. Okay, so I'll put it there. The py has the other electron, and the pz is totally empty, right? So now I have to put, well, but I have to make 4 bonds, okay? Right, because I need 4 hydrogens. So I don't have 4 unpaired electrons right now. So okay, maybe I can say, okay, let's promote that electron to the pz, and so we also have now this situation, right? The 2s has 1 electron, and then one of each electron in px, py, and pz. And then you bring in the hydrogen, right? And you draw the 1s, which again is spherical, right? It's a circle. And then you put the 1 electron of that 1 hydrogen there to pair. So when you do this, 1s, right? You notice something is already off. My structure is supposed to be tetrahedral, okay? But right now, just using the existing orbitals of carbon and hydrogen, I can't get tetrahedral because this is 90, okay? This bond angle is 90, okay? So this is not, carbon cannot just use its own orbitals in order to make the bonds with hydrogen. It must first need to hybridize, okay? So now let's talk about what that is, okay? So we've already shown, can't do it, right? That was the point of that example, is that things need to hybridize. Most central atoms need to hybridize. And then some surrounding atoms need to hybridize as well. And I'll tell you guys what the rule is for that in a second. But let's go back and turn this, since we know it's tetrahedral, let's turn it to 3D. Okay, it's always good to do a 3D version when you're doing bonding scheme. Okay. So now, again, I'm counting, right? 1, 2, 3, 4. I have 4 electron groups, and the rule goes like this. If I need to make 4 bonds, I'll need to hybridize 4 atomic orbitals. Okay. So 4 electron groups means I need to hybridize 4 AOs. AO stands for atomic orbitals. So I'm carbon. What are my 4 atomic orbitals that are available to hybridize? Well, the S and all 3 of the P. That's 4, right? So I circled it. I need to hybridize all of these. Put it in the blender, basically. So hybridization is just like, what is it? When a horse and a mule mates, it makes a donkey, right? And then the donkey is sterile. That's what hybridization is, okay? In biology, right? So here, it's kind of similar. Of course, it's a mathematical thing, but it's basically all of these functions mixed together, and it forms something new, okay? So you're basically putting 4 atomic orbitals in, blending it, mixing it, and you have to have 4 out. Okay, so I'm gonna draw the 4. Okay, so 4 in, 4 out. It has to be conservation of mass, right? And what am I calling these new hybrid orbitals? sp3. Okay, nice and simple, right? Because they're composed of what? 1 s orbital. The mix inside the mix was what? 1 s orbital and 3 p orbitals. So the new orbitals are all called sp3, and they're all 4 of them. right? So 4 in and 4 out. That's how I remember it. If you need to blend 4 atomic orbitals, you need to have 4 hybrid orbitals. Okay, conservation of mass again. Okay, so once you have that, you put in the valence electrons of carbon into this picture, into the new hybrid orbitals. Okay, so I have 4 valence electrons for carbon, and remember all your rules. 1 in each first, right? Don't be the creepy person in the bus before you pair. So 1, 3, 3, 4, right there. Okay. Once you have the mixing done, to get the bonding scheme, just draw the central atom first. So that's carbon. Okay. And then look at the geometry that you put earlier, right? So we have 4 electron groups. The electron group geometry is tetrahedral. So you're gonna put each of these orbitals, hybrid orbitals, look like this. It looks like half of a peanut. Okay. All hybrid orbitals look like this. They won't look any different. Okay. So you need to put 4 of these, right? Each one of these look like this in a tetrahedral shape. So you go like that. Okay, see that? Each one of these is called an sp3. Okay, so label it. Okay. And each sp3 has 1 electron in it, okay? So at this point, when you get to the bonding scheme, all you're doing is you're taking information from all of the legwork that you did earlier, right? Here's your preparation work, and you're just basically just reading off of what you had already done. So 1 electron in each of the sp3, and then you look at your 3D structure. There's a single bond between the carbon and the hydrogen. So the hydrogen needs to come in there with its 1s. And what does s orbital look like? A circle, right? So kind of draw a hydrogen like right there, kind of next to it. And then when you draw the circle, make it overlap with the sp3 orbital of carbon. And then put in hydrogen's 1 electron. And the electron has to go opposite spins, right? Here's the second hydrogen, same thing with its 1s orbital. Right? Third hydrogen. And fourth hydrogen with its 1s orbital, also donating that electron. Okay. So now I have the correct bonding scheme for CH4. And notice that I'm showing the correct bond angle here. It should be 109.5, right? And say not like 90 here, right? So that's why it's good. Always start with the 3D. And use the 3D. See how the bonding scheme is looking like the 3D, only in the 3D there are sticks. In the bonding schemes, instead there are orbitals. It showcases the orbitals, right? Okay. So yeah, that's basically what you're doing for valence bond theory, is showing the bonding scheme and showing exactly what orbitals are forming that bond. So we can say that for the CH single bond, it's the carbon's sp3 that's bonding with the hydrogen's 1s. Okay? That's how we describe that bond. Okay. The carbon's sp3 hybrid orbital with the hydrogen's 1s atomic orbital. Right? Notice we didn't have to hybridize hydrogen. Okay, it's not necessary for the surrounding atoms to be hybridized unless it's making more than 1 bond. Okay, so let's write that rule down. Okay, central atoms will hybridize. Okay. Surrounding atoms will only hybridize when it's making more than 1 bond. Okay, so remember that rules. Central atom will always hybridize. Surrounding atom making more than 1 bond will also hybridize. All right, let's go back to the slides. Okay, so we just showed that, there's a reason why CH4, the carbon, had to hybridize, right, in order to make the bond, because the angles weren't right with just carbon's existing orbitals. Okay, so that's really like the central theme of valence bond theory, but there are a couple more points. Okay, so the basic principle of valence bond theory is that when a covalent bond forms, um, there are going to be two overlapping orbitals, and that overlap region is where the pair of electrons is going to be, and that's where potential energy is going to be lowest, right? AKA the highest probability of finding the shared electrons there. So in quantum mechanical terms, what does that mean when orbitals overlap? It's basically when two of the wave functions are in phase or are at constructive interference. Remember that? Waves that can interfere, right? So we just simplify it by saying overlap, but mathematically, that's what's going on is you got two wave functions adding each other, right? They're in phase. Okay, the three main principles of valence bond theory. Number one, um, uh, the pairs of electron, right, need to be of opposite spin. That's Pauli exclusion principle. So that's something you're familiar with already. So in the region of overlap, make sure that you put one up and one down for the electron. Number two, maximum overlap of bonding orbitals means that you have a more stable bond, aka a stronger bond, right? So the greater the orbital overlap, the stronger the bond is going to be. And number three, hybridization of atomic orbitals. So as you can see in carbon's case, right, its existing orbital could not form the correct angle to bond, so it needed to hybridize all of its orbitals, all of the one right, one of the s orbitals and all three of the p orbitals need to hybridize in order to make the tetrahedral shape. Okay. So that's what we call mixing or hybridization, is the atomic orbitals come together and then they make new orbitals called hybrid orbitals. Right? Okay, so let's talk about the maximum overlap. Remember, maximum overlap means most stable and also the stronger the bond, right? So if you see that two hydrogen atoms are bonding together, remember each hydrogen is a 1s orbital. So how are they going to overlap? Well, they just collide straight on, right? And you have this overlap region right here. So for spherical orbitals, you really have a maximized overlap. So it forms a very strong bond. Okay. When you have, say, hydrogen and fluorine come together, fluorine has a 2p orbital, right? So it's right, it's a peanut here. And so the 1s of the hydrogen just plugs into the 2p like that. Again, you have a very good overlap here as well, right? But not as good as in the 1s and 1s. You can see that, right? The region of overlap here is a lot bigger, right, than here, right? And the larger the overlap region, the stronger the bond. If two fluorines are bounded to each other, like in fluorine the element, right, F2, then you got two p orbitals doing a head-on collision like that to have overlap. Okay, now that overlap is going to be weaker than this because now you have just two smaller peanut lobes overlapping instead of like a nice huge 1s, right? Nice spherical 1s. Okay, but all three of these are considered a single bond, right? Because it provides region for two electrons to be in, right? Two electrons as a bond. So all of these are single bonds. Okay. All right, now we get to hybrid orbitals. Okay, hybrid orbitals, again, right, just means you're mixing them together. Wave functions are colliding in phase. And the types of hybrid orbitals, you only need to know 5. Okay, so types of hybrid orbitals or hybridization, if you get, a question on the quiz or exam and it asks for what is the hybridization of this molecule, this is one of your 5, answers, right? One of these. So if you only have one S and one P mixing, well, it's easy. It's called SP, right? So it's very, very easy to remember. If you have one S and two P's mixing, then it's called SP2. right? If you have one s orbital and three p orbitals mixing, then it's called sp3. If you have five orbitals mixing, then it's called sp3d. Well, why d and not sp4? Well, remember, we only got three p orbitals, right? So when we use all three, we need to introduce another one. So that would be the d, so sp3d. And then we also have sp3d2. That's if you need six bonds, right? So we need to make six bonds or six electron groups, right? So lone pairs too, right? So if you have six electron groups, it's going to be sp3d2. Okay. Again, why did we put another d orbital? Well, we need six, right? So if you add up these little superscripts, right? This is an implied one, right? Well, these are implied one. The superscript should add up to the same number of electron groups. So let me show you the pattern to know for that. So hybridization is all about electron groups, right? And you guys already know how to count electron groups, so let's remind ourselves. A single bond is one electron group, right? A double bond is one electron group. A triple bond is one electron group. And a lone pair is one, right? Everything's one, okay? So you just have to count, and it's always around the central atom. If around the central atom, you just have two electron groups, remember the electron group geometry is linear. And your hybridization will be sp. Because what does that mean? You only need to hybridize two orbitals. What are the two lowest energy orbitals? S and a p. Okay. And how many sp orbitals are there? The number of hybrid orbitals. Two. And what do they look like? Um, half of a peanut. Or students in my past class, I've called it like a flower petal. Okay. So all hybrid orbitals look like a flower petal regardless of their hybridization. Okay. But how do you know how many of them there are? Remember, it's just adding up the superscripts. So one and one is two. Okay. If we have three electron groups, okay, electron group geometry is trigonoplanar, and our hybridization will be sp2, right? Because we need three atomic hybrid orbitals, or sorry, three atomic orbitals to hybridize. So one s and two p. And then how many hybrid orbitals do we have? Well, it's gonna match with the electron group, right? Three. We'll have three. There are three sp2 orbitals. Okay. Always. If it's four, then we got tetrahedral, and then we need another p orbital, so that's sp3. Okay. And how many sp3 orbitals are there always? Four. Okay. Right? Because it's basically how many came in to mix 3p and 1s, right? So for conservation of mass, right? Once we get to five, it's electron group geometry is trigonal bipyramid, and hybridization will be sp3. We need to introduce, right? We'll use all the three, all three p's. So we need D, sp3d, and we will have five of those. Okay, right? One of the s, three of the p, one d. So that's total of five. For six, it's octahedral and sp3d2. So you will have six of sp3d2 orbitals always. Okay, and look, they all look the same, right? So just keep it simple. Okay, so just take this table and just remember, right? Remember that all these are connected together. Electron group geometry is connected with geometry and is connected with hybridization. Okay, so once you get to your Lewis structure and you look at your central atom, you already know the hybridization because you can already see how many electron groups are there. Okay, and once you know the hybridization, it's really easy to draw the bonding scheme. Okay. All right, so let's put this one aside and let's do some more examples of bonding schemes. All right, so let's first do this very simple one. BeCl2. I would always start with the Lewis structure, right? And the 3D one. Okay, you want to make sure that everything looks legit, and you're not being fooled by the bond angle or the shape, right? So make sure you draw it in 3D. So once we have the Lewis structure drawn, look at the central atom, and you can see that there are two electron groups. So already you know that the electron group geometry is linear. So redraw it if you had drawn it, differently before. Redraw it so that it is linear, straight across, right? So now that you know that there are two electron groups, you already know what hybridization is associated with that, right? Two electron groups means sp, right? So then one of the s will mix with the p, one of the p, and become two sp hybrid orbitals. Remember, there's always two sp hybrid orbitals, right? Conservation of mass. Two in, two out, right? And notice too what it looks like. The sp orbital looks both like its parents. That's why it's kind of like hybridization, in biology, right? The kid looks like the parents, right? You have like a spherical s orbital with like a peanut shape p orbital. When they mix, you have kind of both, right? You have this little knob right here that looks like the peanut, and you have this thing, mushroom thing, that looks like the s, right? So that's the mix. But when we draw it on the board, we don't include the little knob here. So that's why it just looks like a flower petal, right? That's your flower petal right there. Okay, so we just draw it like that. Okay, so now how should these two sp hybrid orbitals arrange around beryllium? Well, the answer to that is in your geometry, right? We're going to put it linear, so opposite each other. So now it looks like that. Okay? So 180 from each other. Okay. So in the end, and then we have chlorine, right? So chlorine has one p orbital um, that has an electron in it, and that's the pz. And so you just show the pz of the chlorine plugging in with the sp, okay, on either side, right? And that's how it's forming that single bond between the beryllium and the chlorine, right? Here the px, so the py and the pz is also shown on beryllium, but it's empty, right? So according to me, you don't even have to put it in there, right? You just show the ones that are making the bond. Okay. Okay, let's do BF3 together on the board. And the question would be like, draw the bonding scheme for BF3. Okay. Remember, always start with the Lewis structure. 3 plus 3 times 7, that gives you 24 valence electrons. So boron, fluorine, chlorine, chlorine, single bonds at 6 electrons used, got 8 electrons left. Like that. And that's my 18. And I check for octet. Fluorine has octet. Boron does not. It just has 6. But remember, it's okay because it's left of group 4. So we're good for quote unquote octet, right? Check the form of charge. Fluorine 0. Boron is also 0. So that really is our structure. Okay. And once I have my structure, then I go into the central atom and count the electron groups, right? This is step by step here. 1, 2, 3. So I got 3 electron groups. Okay. And right away, I do the electron group geometry. Once I get the electron group, do the electron group geometry. This is the homework to make your bonding scheme just fall in your lap later, right? So do the legwork here so that it gets easier when you start drawing the bonding scheme. So what is 3 electron groups? Electron group geometry, trigonal, planar, right? And so then I look back at my picture. I'm like, is it trigonal planar? Is my picture actually showing trigonal planar? Yeah, because remember, trigonal planar is 120. Okay, so it just so happens in this case that my Lewis structure is already in 3D. That's not going to be the case. In fact, most of the time, that's not going to be the case, right? So I just got lucky here. Okay, so I could keep my picture, great. And now I do orbital diagram. right? So that's really step, step one, let's get that. Step two here, right? And step three, I do my orbital diagram for everybody. Start with the central atom, which is boron. And I do the short one. So it's 2s2. 2p1, is it? Okay. Yeah. So, you guys know how to do this already. That's why we learn all this stuff first, right? And to kind of build up to this very technical and sort of beautiful way of looking at how bonding is. This theory is actually quite advanced, so it's really cool that you guys are at that point where you can learn this and understand this. And at the beginning of this semester, right, you barely knew what an electron was. So I always like to take a minute to see how far we come, right? So everything that you learn now is culminating together so that you can do this, right? So orbital diagram, electron configuration, right? Just learn that. Go to fluorine, got 3 of them. Just do it for one, right? Because all of them are the same. So it's 2s2, 2p, fluorine's 5. Remember Hunt's rule, so 1, 2, 3, 4, 5. Okay. And then remember, we call this XYZ, right? XYZ across. Okay. Okay, now at this point, you're going to figure out what the hybridization is, right? And it's easy to just go off of, remember electron groups, remember that table, right? It's all off of the electron group, so it's 3. So that means I have to circle 3 boxes, right? If it says 3, then circle 3 boxes. 1, 2, 3. Don't circle that one, okay? And then I mix it, right? So this is step 4, is I mix, okay? And I get the result. Okay, if I circle 3, I should just have 3 out, right? 3 in, 3 out, conservation of mass. Draw those stuck together. And what do we call these new hybrid orbitals now? Well, simply you use 1s and 2p, so sp2. Pretty simple, right? And there are always 3 sp2 orbitals, right? So there they are, okay? But there's still this orbital here that was unhybridized. So put it off to the side, not stuck with these. And that is your PZ, right? Remember, XYZ. So label it all nice. And now you put in the valence electrons, right? So we can say step 5, put in the valence electrons of the central atom. Okay, it's all about the central atom, right? So boron has 3. I'm going to put it 1, 2, 3. Okay, remember Hund's rule, right? 1 in each person. Now I'm ready for the bonding scheme once I get to this part. So my bonding scheme, always start with the central atom, so that's boron. Okay, and now I need to draw in the hybrid orbitals onto boron. Remember, all hybrid orbitals, they look like this, right? Okay, but there are 3 of them, so I gotta put it 3 around boron. But how should I do it? Well, you did your homework earlier. How should I do it? Trigonal planar. Or like this, just copy your 3D, right? 1 here, right? Basically 1 here, 1 here, 1 here. So it's gonna look like boom, 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 boom. Those are my 3 sp2 hybrid orbitals, okay? They each have how many electrons in there? 1. So just do it. Show that, okay? I also have a PZ hanging out, empty. So I draw that one in there too. And P orbital looks like that, right? So I call that the PZ. Can get a little messy here. So actually I could probably do that better. So I will. So I'll label it up here instead. Okay. And then I'm gonna make this axis the z-axis. Right? At this point you can choose. Right? So I'm gonna make this my z-axis. It's my PZ coming in there, right? That's the other part of the PZ. And it's empty, so I don't put any electrons in there. But I still show the orbital, right? Yeah, so this is my sp2. Okay, now I go to the fluorine. And I look at which orbital only has 1 electron, because I know that's the one that's going to overlap with boron's sp2. So which one is it? It's the PZ of the F that has a single electron. So I draw F here, okay? And then I'm going to draw half of that p orbital, and the other half, I call that pz. And the pz has one electron in it. That's the one that pairs with boron's sp2. Okay. And how many times does that happen? 3 times. Okay. So yeah, my board space is leaves something to be desired here, but okay, you get the point. So I can draw F here. That's F's PZ with another electron. Okay, and then over here, another PZ of the third F, third fluorine. Okay, so I'm describing this, right? This single bond between the boron and the fluorine. Okay, using orbitals, right? That's just what a bonding scheme is. Okay. And looks like I'm almost done. On one of the Fs, I would like you guys to show the lone pairs, but not on the other Fs because it looks really busy. Okay, because check this out. I draw the 2s in there on the fluorine, that'll be like a circle, right? Spherical. Put a lone pair in there. And then my px and py also have lone pairs. So if I call this the z-axis, I could call this the x-axis, and I could call this the y. So I'll call this the px, I'll call this the py, and they have lone pairs in there, right? Boom, 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 boom. Okay, so each fluorine has a lone pair. Sorry, 3 lone pairs and 1 bond. Okay, I don't need to show it for these fluorines. Just do it for one of the fluorines, right? Because as you can see, it gets messy. And I do want you guys to label, because as you can see, they all just look like flower petals, right? Even the p orbitals. So I want you guys to be very diligent at labeling your orbital so that it doesn't confuse you for once. For one, and that's important, and it doesn't confuse me when I'm reading. So label everything, okay? And so that's your bonding scheme for BF3. All right, let's do NH3 now. Okay, so 5 plus 3 times 1, 8 valence electrons. Nitrogen is going to be in the middle. Hydrogen like that. Single bonds. 2, 4, 6. I need 8, so 2 more on the nitrogen. And all of a sudden, I see that it's 4 electron groups, right, guys? 1, 2, 3, 4. That's 4 electron groups. I already know the electron group geometry for 4. It's tetrahedral, right? From last lecture, right? You guys should be well versed in it now, okay? And then I look at the picture and I'm like, wait a minute, that doesn't look tetrahedral because tetrahedral has bond angle 109.5, right? That looks like 120. This is not 3D, okay? So I redraw it, okay, in 3D. Using the tetrahedral template. Remember, tetrahedral templates like this. Okay, so you have H, 3 hydrogens. This one's just a lone pair, so I can just erase that bond and just put a lone pair. Okay, but it's off of the tetrahedral template, right? So know your templates. You can draw it in 3D. This is going to help you draw your bonding scheme again later, right? Next thing you do, orbital diagram, right? Nitrogen, brackets, helium, right? Brackets helium, 2s2, 2p3, 1, 2, 3. Okay. And then hydrogen, easy, is 1s1. Okay. All right, so now that I have all that, figure out the hybridization. I figure out the mixing. Again, it's based off the electron groups. That's why I get it first, right? 4. That means I need to circle 4 boxes of nitrogen. Well, that's the 4. That's my 4, right? And then I mix it. 4 in to the blender, 4 out. And they all look the same, right? And they're all called the same thing. They're called sp3, right? Because I use 1 s and 3 of the p orbitals. So each of these is called an sp3. Okay. Then I put in nitrogen's valence electrons, right? It's all about valence electrons bonding. So 1, 2, 3, 4, 5. Okay. So we can see that in one of the sp3 orbitals, you have a lone pair, and then the rest of them you have singles. Okay. So we can draw that, right? Let's see what that looks like now. Bonding scheme. Nitrogen, draw that first. Okay. And then I know that I need to draw 4. What do they look like? Flower petals. 4 of these flower petals around nitrogen. But in what manner, in what shape should I do it? In what geometry? Well, I did my legwork. It's a tetrahedral, right? So it's gonna look like that. Okay. So 1 is gonna house the lone pair up there. 1 is here, right? That's why I draw my 3D structure. I kind of use it to get my bonding scheme. You see how similar they look, right? And then I know that one of them has a lone pair. It's that one on top. And then the other 3 have singles. Okay, that's why I did all the prep work, right? To get to this point where it's really easy to see how to put the flower petals on there and also how many electrons are in there. Okay, so that's all from here, right? Then I look to what's going to be bonding to the nitrogen. Well, 3 hydrogens, right? And what orbital does the hydrogen have? 1s, just a circle. So go to the singly occupied one, put the hydrogen there, draw the circle so that it overlaps with the sp3, and then spin down for that 1 electron of hydrogen, sharing with nitrogen's sp3. Okay, so beautiful. That's my bonding scheme for NH3, showing single bonds, right? Overlap regions to make the NH single bonds, and then showing also that 1 sp3 hybrid orbital that's housing the lone pair. Okay. Okay. So simple enough, really, right? As long as you follow those steps, make sure you have 3D structure, and then knowing your hybridization. Okay. And after that, it's just cut and paste basically onto this bonding scheme, all the information that you have. Okay, let's do another one. Just knock out a whole bunch, right? Let's do H2O. So that's 6 plus 2 times 1, 8 valence electrons. So oxygen, something like that. Okay. How many electron groups? 1, 2, 3, 4. So again, we have the electron group geometry of tetrahedral. Right, next thing we do after we get electron group geometry, we're like, is that looking tetrahedral? No, it looks linear. You see, your starting Lewis structure is always mostly, most of the time it's gonna be crap. So always redraw in 3D. In 3D tetrahedral template should be like this, right? Right, it's bent. It's got 2 lone pairs. Okay, so it's gonna look like that. Then we do the orbital diagram of oxygen, 2s2, 2p4. Then hydrogen, of course, is just 1s1. Okay. Then we do the hybridization, the mixing. Remember, it's always off of electron groups. That's 4 electron groups. So I gotta circle 4 boxes, always like that, right? And mix it together. If I circle 4 boxes, then I gotta spit out, right? I gotta make 4 boxes on the other side, all stuck together. They're all called what? sp3. Okay. And what do they all look like? Like that. Okay. So now we go in, we get the valence electrons in there first. Oxygen has 6 valence electrons. So 1, 2, 3, 4, 5, 6. Okay, and we see that oxygen now has what? 2 lone pairs and then 2 singles, right? Great, because this needs to make 2 bonds. Okay, so our bonding scheme is going to look like this. I need to draw 4 of these. How should I draw it around oxygen? We could do this, right? Okay, and sorry, not bonds, like this. Okay. And 2 lone pairs, singles here. And then probably should make this more angled so it looks like 109.5. So we'll look at like that. Okay, that's good. And then we label these sp3, 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 sp3. And then we go in with hydrogen, right? Hydrogen has a 1s, which is just a circle. So here, and then hydrogen's 1 electron is gonna pair. Label it 1s, label 1s. Hydrogen's 1 electron is gonna pair. Okay. So now we've described the OH bond, right? Single bond here, and the lone pairs of house in the sp3 hybrid orbitals of oxygen. Okay. So not too bad, right? Really the same steps every time. Okay, let's do a PCl5 next. That's 5 plus 5 times 7 is 40 valence electrons. Central atom, P, bond, 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 bond. That's 10 electrons used. 30 left. 6 on each chlorine. That's 6 times 5, that's 30. So that's it. Now I check for my octet. Chlorine has octet. Phosphorus has 2, 4, 6, 8, 10. It has over an octet, but that's okay because phosphorus is in period 3. So octet is checked. Formal charge 1, 2, 3, 4, 5. Phosphorus should have 5, so that's 0. One of the chlorines 1, 2, 3, 4, 5, 6, 7. So 0 as well. So that's great. That's our structure. Now count the electron groups, right? 1, 2, 3, 4, 5 around the central atom. And the electron group geometry is for 5, it's trigonal bipyramidal. Okay. So remember the template for that. Remember the template for trigonal bipyramidal? And we need to redraw it in 3D. It looks like this. Okay. Okay. But lone pairs on there too. Okay. Beautiful, right? Trigonal bipyramidal. Know your templates, okay? All right, now we do our homework. Orbital diagram for phosphorus. Looks like brackets neon, 3s2, 3p3. Okay. Then we do it for chlorine, the surrounding atom. Chlorine is also in period 3, so 3s2, but 3p5. Okay. All right, then we do the hybridization. Let's see, we need 5 electron groups, so therefore we need to circle 5 boxes. But right now we only have 4 boxes for the central atom, right? There's only 4 boxes. We need another box. Well, what comes after P, everybody? D. So you're actually gonna take, there's actually 5 here. That's empty, right? It's just sitting there. Phosphorus has them. It's just empty, right? So you're gonna take one of them. Okay. So what do you get? 5 boxes out, right? And this is called sp3, right? A hybridization. Okay. They all look like this, right? And there are 5 of them. Then you fill in the valence electrons of phosphorus. That's 5. So 1 in each. Okay. Now you're ready to draw the bonding scheme. So bonding scheme. Phosphorus in the middle. And then I know I need to draw 5 flower petals. How should I do it? Trigonal bipyramidal. Using this as your template, right? So basically flower petals where the bonds are, right? Okay. So it's going to be like this, that, like that. Okay. 1 electron on each. Right, and label them. sp3d, 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 sp3d. Then the chlorine comes in, right? Which orbital of the chlorine is going to bond? Well, there's only one. It's this one here that has an unpaired electron. That's the 3rd one. We call that PZ, right? So I can just draw the chlorine right here with its PZ orbital, right? PZ, remember, it's a peanut, right? So we got 2 lobes, one here on this side, one on that side. Donates that 1 electron. Okay. I can even show the other orbitals, 3s right here. That's a lone pair. And then my px and py have lone pairs as well. So we'll go px as a lone pair, and py as a lone pair as well. Okay, just show that for 1 chlorine. You don't need to show it for all. And then here, another chlorine with its pz, and then 1 electron. Here, another chlorine with a pz, 1 electron. Another chlorine with its pz, 1 electron. Another chlorine here with its pz, and 1 electron. Okay. There we go. That's the bonding scheme for PCl5, right? Yeah, should be able to see that. Zoom in and hopefully see that. Okay, so done lots of examples, right? You guys should kind of have an idea, right, like a groove of the steps to follow to get to your bonding scheme, okay? Don't just jump straight into it. Do all your homework first, right? Do all these steps, and then the bonding scheme just really falls into your lap that way. Okay. Okay, let me show you guys now what happens when we have double bonds. How does the bonding scheme look like now? So let's do an example with C2H6. Actually, C2H4. So we got 2 times 4 plus 4 times 1. That's 12. Okay. Notice you see already we got 2 central atoms, and then spread the hydrogens evenly around. So spread it evenly around, 2 on each carbon. Reduce single bonds everywhere. That's 10 electrons used. 2 electrons left. Where are we going to put it? The inner central atoms. So that's it, right? But right now this carbon doesn't have octet, so I'm going to move these 2 electrons, make a double bond. Now everybody has octet, right? 2, 4, 6, 8. Good octet. Check formal charge. This carbon 1, 2, 3, 4, 0. This carbon 1, 2, 3, 4 should have 4, so 0. Okay, so we're good to charge. And now we do the orbital diagram, right? Or we do electron groups around the central atom. Since there are 2 central atoms, you need to do it for both, but luckily both of them are exactly the same, right? You can see that. So that's 3 electron groups, right? Just concentrate on 1, 1, 2, 3. The other is the same, right? 1, 2, 3. So both have 3 electron groups. And what is the electron group geometry? Trigonal planar. Okay. Now we do orbital diagrams. So for carbon, it's 2s2, 2p2. For hydrogen, 1s1. Great. Okay. Then we do the mixing. Look at the electron groups. That's 3. Circle 3 boxes. Mix. 3 boxes in, 3 boxes out. What do we call them? sp2. Right? And then you got the one left over here. Don't ignore it, right? Put it over there still. Which one is that? That's the pz. Then you put the valence electrons of carbon through all of them. That's 4. So 1, 2, 3. Remember Hund's rule, all the way across, and then pair. So 1, 2, 3, 4, like that. Now you're ready for your bonding scheme. Draw the central atoms, right? They're both the same. They're both sp2. So draw them both like that. Okay. And then draw the 3 sp2 on each of them. So on the left carbon, if I was to draw 3, how should I do it? Trigonal planar. And just copy that. Right? So 1 over here, 1 over there, and 1 over here. Sorry, I should make it look a little bit pretty. There we go. And then for this carbon, same thing, right? Oh, that one's overlapping with that one. That's great because we need that to make that CC single bond, right? So up and down. So all of these, let's label sp2, sp2. Okay. And they got 1 electron in each. Okay. And this one already paired with that one. It's already making a bond. Okay. And then after that, we do plug in the hydrogen where there's single electrons. So hydrogen is going to bond there. Hydrogen is going to form a bond here, right? With its 1s. Right. So now what we've done is we've described all the single bonds, but we know there's a double bond there too that we haven't described. Well, we also need to draw in the pz orbital of carbon, right? So let's choose that as our z-axis, right? This whole thing's pz. This whole thing's pz, and it's got 1 electron in each. Okay. So how is it going to form? How's the overlap going to be to make that second bond? Well, you see, both of these are parallel to each other, right? So the overlap is like this. It's a side-to-side overlap instead of a head-on overlap like we've been seeing, right? Now, this lobe is going to overlap with that, and this lobe is going to overlap with that. But we can't show it how, on this board here. In real life, they're actually touching. But we can't show it on the board, so we just tether it with this dotted line. So both the top lobe and the bottom lobes are overlapping, right? So make sure you show dotted for both upper and lower lobe. Okay, so that's going to be our second bond. Okay. So when you have a multiple bond like double or triple, you also have to label whether it's a sigma or pi bond. Okay, so let's quickly go over bond types. Okay, we have sigma, which we call head-to-head type bond. Okay, and that's like if you have a 1s orbital with another s orbital. It doesn't have to be 1s, it could be 2s too. When they overlap with no interruption, that's called sigma. And probably sigma like s, right? That's why it's called sigma, because it's like s. But you can also do it with s and a p. So an s and a p would look like this. Right. And there's the overlap region, right? That's still a head-to-head overlap. And then you can also have, start by this. A P overlapping with a P, right? Head to head like that, okay? So all of these types are sigma bonds. And that's as opposed to a pi bond, which is not head to head, but it's a side to side bond. So pi, like P, okay? Two P orbitals can do it side by side. Okay, you see they overlap, okay? But that's a P with a P, okay? But there's an interruption, okay? So pi bonds have an interruption. There's overlap, no overlap, and then overlap again, okay? Now d orbitals can do it too. So d orbitals, remember they're like double peanuts or four-leaf clover. They can do it with a p orbital. See overlap there, okay? So again, overlap, interruption, overlap, okay? So you see the difference between the sigma and the pi bonds, okay? Guess which one's stronger? The one that doesn't have interruption, right? Here you got a weak link here, okay? Here you have no, just like a continuous overlap, right? No interruption. So sigma bonds are always stronger, okay, than pi bonds, right? Sigma bonds always greater than pi bond strength. Okay. So going back to this picture now, okay, what type of bond is this? Oh, that's no interruption. That's sigma. So label on your bonding scheme all the types of bond. That's a sigma bond. Sigma bond. Here between the carbon, we have one sigma bond. It's between the sp2 and sp2 orbital of each carbon. And then we have the pi bond, right? You see that? That's this dotted line here, right? Shows a side to side overlap. And that's a pi bond. Okay. That's half a pion, that's the other half, right? Together is one pi bond. Okay. So there we go. This is your bonding scheme for C2H4, which involves a double bond, right? Let's see it for triple bond. What does that look like? So we'll do C2H2 now. C2H2, 2 times 4, that's 2 times 1. 10 valence electrons. We got carbon, carbon, hydrogen, hydrogen, single bonds, 2, 4, 6, 4 left. So I'm gonna do it like that. But I see this needs to make 2 more bonds. So double bond. Oh, still not good octet. So a third one, right? And then how many electron groups around the subatoms? There are 2 subatoms again, but again, they're identical. So that's great. So 2 electron groups, right? 1, 2. And electron group geometry for 2 is linear. Right? So I look at my structure. Is it linear? Yes, it is. Coincidentally, we have another case where we coincidentally got it right. So we don't have to redraw it. That's great. Now we just have to do orbital diagram, right? So for carbon, it's 2s2, 2p2. For hydrogen, easy peasy, 1s1. Then we do the mixing, right? How many electron groups? That's 2. So circle 2 boxes. Which 2? The first 2. Say mix. 2 in, 2 out, right? 2 out. And then there are two unhybridized stuck together, right? These two. So what are these two called? Well, just one S and one P, so it's SP. Right, those two are SP. These two, they're different, right? This one is the PX, PY. This is PX. PX got hybridized, right? See how PX got hybridized? PY is unhybridized, and so is PC. So there we go. All right. Now we put the valence electrons in, right? Carbon, it's always about the central atom, 4. So that's 1, 2, 3, 4. Okay. And now we can draw the bonding scheme. Okay. Draw your 2 central atoms first. Okay. And then figure out the situation with your flower petals, right? I know I need to put 2 of them on each carbon, but in what manner? Linear. That's why I did that, right? So that's just here and here. And same thing with the other carbon, that and that. So that's the overlap, right? So 1 electron up and down. The other ones have 1 in each. Okay. And I also draw in the PY and PZ, okay, on both carbons, right? So I can do like this. And like this. Call this one the PY. Call this one the PZ. And 1 electron. Same thing over here. E, Y. Okay. 1 electron in each of those as well. Okay. And then I put in my hydrogen. Well, the hydrogens are gonna be here, right? Look at my Lewis structure I did with the 1s. Okay. Okay, so now I've described the single bonds of the CH. What about the other 2 bonds? Oh, what do I see? Oh, the PZ come together side by side, and the PYs come together side by side, right? So this is a sigma bond. This is sigma. This is sigma, but this one is pi, and this one's pi. So how do we describe the C triple bond C? One of them is sigma, the other 2 pi, right? See that here. So that's how you do triple bonds, okay? So notice in the 2 cases now that we've done it, where you have multiple bond, the always one of them is a head-to-head. Always one is sigma, and the rest are pi. And the pi bonds are made by the unhybridized bonds, right? It's the unhybridized p orbitals that's forming those pi bonds. Okay, so often that's what you're gonna see. Alrighty, let's do another one last example. Let's do H2CO. That's 2 times 1 plus 4 plus 6. So we got 12. Carbons in the center, put hydrogens here, oxygen there. Have single bonds, 6 electrons used, 6 electrons left. So we have put it there, and we realize, oh, we gotta make this octet. So we're gonna raise 2 and double bond. Right? Everybody has octet now, yes. Do formal charge 1, 2, 3, 4. That's 0. On this oxygen, 1, 2, 3, 4, 5, 6. That's okay. Hydrogen obviously 0. Right? Now we can do electron groups. So again, focus on the central atom. That's 1, 2, 3. 3 electron groups. So what is the electron group geometry? This is for the carbon, by the way. Sure you don't play it. All right. But you guys remember the rule that I had earlier? Central atoms always hybridize, but surrounding atoms that's making more than one bond also hybridize. So here we have a case where our surrounding atom is making more than one bond. So we also have to figure out oxygen, right? So oxygen, how many electron groups? 1, 2, 3. So oxygen's is also trigonal planar. Okay. So now we do our orbital diagrams. 2s2, 2p2, do oxygens, 2s2, 2p4. Okay, and then hydrogens, still 1s1. Okay. All right, let's hybridize carbon first. The number is 3. So circle 3 boxes. We'll mix. 3 boxes in, 3 boxes out. What do we call them? sp2, right? There's 1 box that's not mixed. Put it off to the side. Which one is that? What unhybridized orbital? PZ. Okay. We put valence electrons in there. Carbon should have 4, right? 1, 2, 3, 4. 1, 2, 3, 4. Remember, now oxygen needs to hybridize too. Even though it's a surrounding atom, it's making more than 1 bond. And what is oxygen's electron group? There are 3. So we also circle 3 for oxygen. We make it mix. And then 3. Okay. There's still 1 left for oxygen. Let's call that, right? We call that PZ. And oxygen has 6 valence electrons. 6. So we go 1, 2, 3, 4, 5, 6. Okay, so now we're ready for the bonding scheme. Okay, so I'm gonna do the carbon first, right? Carbon. I'm trying to put these orbitals onto carbon. So for sp2, how should I do it? Well, sp2 is associated with what geometry? Trigonal planar. And also I already did that homework up there, right? Trigonal planar. So I'm gonna make one go like that, one go like that, one go like that. Basically copying what I have here, right? And this was already actually my 3D structure. So that's why I didn't have to redraw it, right? It's already in trigonal planar. So I'm just placing the orbitals where those electron groups are, okay? And then 1 electron in each, right? According to this, 1 electron in each. And then carbon also has an unhybridized PZ orbital that I also have to put on the bonding scheme. So the p orbital is a peanut, right? It has a top lobe and a bottom lobe. So I draw it like that, and I put 1 electron in it. Okay, so I'm calling that the z-axis. Okay. All right, I'm done with carbon. I'm going to do the same for oxygen. So oxygen is going to be bounded to carbon. Okay, and oxygen also has sp2 hybridization. So its geometry is also going to be trigonal planar. So that's how I need to put my 3 sp2. sp2 is as trigonal planar geometry, right? And it just so happens that that sp2 of oxygen has the 1 unpaired electron that it's going to share to make that sigma bond with carbon, right? Oh, let me label these as well. These are all sp2s, right? And then the other 2 sp2 orbitals of oxygen contain the lone pairs, right? And so that's kind of cool. We know where the lone pairs are now, right? We know the oxygen has 2 lone pairs on it, but now with this bonding scheme, we know where they're housed. They're housed in the sp2 hybrid orbitals, okay? Then the oxygen also has a PZ unhybridized orbital, so we gotta draw that on there too. And remember, we already said this is the z-axis, so we need to keep it consistent. That means we need to draw it like this, right? Because that's the z-axis. We've already determined. Okay, so the PZ also has 1 electron in it. And now you guys should already see how that double bond is forming between the carbon and the oxygen. It's the side-to-side overlap of these 2 PZ orbitals. So I'll show that by this kind of dotted bond, the tether bond. Okay, so this is we're showing basically that the top lobes are overlapping and the bottom lobes are overlapping together. That's a bond, right? That's one bond. And then we label it pi bond, right? Here's the sigma bond, okay? And then we still put hydrogens on there. We gotta put hydrogens on the carbon. Well, they obviously go here, right? It's the 1s has one electron in it of the hydrogen that pairs with carbon's one electron. Okay, so the 1s with the sp2 of carbon is forming the sigma bond of the CH bond. Okay, so we got sigma bond here, sigma bond here, sigma bond here, and pi. Okay, so now from now on, when you guys do bonding scheme, you want to label that, right? We just went over, the difference between sigma and pi bond. So you should label all that onto your picture. Okay. All right, so let's go back to the slides. All right, so the sigma and pi bonds, right? We know what the difference is there. Sigma is the head-to-head bond when you don't have an interruption in the bond, and then pi bond is this one where you have a side-to-side overlap and there is an interruption, right? There's overlap, then interruption, then overlap. So that's why sigma bonds are considered stronger than pi bonds, right? So what you're looking at here, right, was the structure that we did earlier, which was C2H4. Here we are shown the computer rendition of what these orbitals look like. So of course the computer is going to be more accurate than what we can do on two-dimensional paper. So that's why we want to look at these models, right? So the computer models the p orbitals as the pi bond, right, as these two unhybridized p orbitals. And in the computer models, you guys can actually see the overlap, right? But the region of overlap is not as big as, say, when you have a sigma overlap, which is in this top picture, okay? And so that's why a sigma bond is stronger than a pi bond. So this final picture, C, shows a more accurate sort of rendition of what the electron cloud, right? So the electrons are spread, the pi electrons are spread over the entire molecule. So it kind of looks like a hot dog, right? So that's kind of what happens when you have a side-to-side overlap. It's like these two p orbitals kind of like merge together, fuse together, and it kind of looks like hamburger buns or hot dog bun, right? If you look at C2H2, you see the same phenomenon where when the p orbitals overlap, again, you get sort of this hot dog shaped cloud. It's basically the electron density is smeared across both carbons, right? Because that's where the triple bond is. It's between the two carbons, right? So in multiple bonds, remember we said one bond will always be sigma, and that's from the two hybrid orbitals of the two atoms. But the pi bonds are formed by unhybridized p orbitals, right? So in C2H2, we also did this earlier. If you look at the bonding scheme, right, that we did, it's the px and py unhybridized orbitals that form the side-to-side overlap for the double and the triple bond. Okay. And so that's why you have two sets of pi bonds here, okay, that you see. So, of course, we are limited by what we can do on a two-dimensional piece of paper with the bonding scheme, right? But this kind of gets to show you what it probably looks like in real life, right? Is this sort of smearing of the electron density over the two central atoms here. Okay. So that's it for today's lecture. I'm going to see you guys for chapter 11, lecture 3 next time.